So this is a very sophisticated audience for some of what I'm going to talk about, particularly around the issues around data, because I think many of you now have been thinking about these very seriously with the Fermat project and the related efforts through the digital infrastructure program that's gotten started here, which is very exciting. And I really expect to follow up in a number of ways, because the work that we need to do here is way bigger than any of our small groups can accomplish. And there's just so much that needs to get done, and we really need to learn from each other, steal the best ideas. So I'm looking forward to continuing discussions. Okay, so I'm going to explain the MGI, as Claudia just said. I'll try to explain some of the details for how an initiative in the US gets set up and what that means, and what the MGI is trying to achieve. And then hopefully a number of you haven't seen or know all of this, otherwise you can relax for a half an hour and then I'll get to some of the newer stuff. Because as I said, mostly what I'm interested in is determining how we can collaborate and what new ideas we can bring to bear on this problem. Okay, so here it is. It's good to be back. Just as a side note, my last trip out of the United States was to visit this program just as it was really getting started. And there was no funding yet. And here I am again. So this is my first trip internationally since they decided that it was safe for me to leave. So here I am. And I'm going to talk about the initiative itself, and then my own organization's role in supporting the Materials Genome Initiative. And of course, the role of artificial intelligence in supporting and achieving the goals of the initiative, and just sort of how it fits in to what I would call our more classical view of materials modeling that many of us grew up with. And then finally, I'll finish with the strategy that was just announced for the US initiative, and what's next, what's keeping me up at night, things like this. Okay. And I don't know how long you want me to talk. I'll try to stop at around 1/4 after. I don't know what is traditional. Okay, so maybe a little less. I'll try to go quick. Okay, so the MGI, right, is the Materials Genome Initiative. So there's no surprise here for this audience. I like showing this picture because it's two pieces of steel cross-section, identical compositions, right? So the only thing that's different is how they were processed. And the ability to predict shapes like this is non-trivial, right? And so what's happened in the last 20 or so years, 25 years, is that this has become much more possible, right, at these sort of more macro scales. So it's one thing if you're doing a computation, for that dot. It's another thing if you really want to go all the way out from, atoms to practical length scales. And so the notion of doing design on materials from the bottom up, and then preferably even the reverse, where you decide what properties you want and then provide the processing conditions as a result of a computation, would be the dream of materials design. And so we're going to talk about some of these ideas. So, in a certain sense, this is a natural evolution of ideas that we've been pushing in science and engineering for a long time. And if you look over here, right, I have a picture of a CAD piece of software, which is now standard in engineering and has been since the 90s for designing things, right, that you would manufacture. But then you go over here and you're looking at a finite element model, which pretty much any engineer as an undergraduate can now use to predict the response of systems to stress and to failure. So we've moved the theory of elasticity essentially into a computational tool that anyone now can use that has sort of modest training. And now down here we have some simulations I did with Hungarian colleagues, or they did, and I just collaborated with them. So this is their work, predicting spherulites in a melt. And so you're starting to predict the microstructure, and of course there are many people who are working at even deeper length scales than this, all the way down to the atoms themselves and the electronic structure. But the point here is that this soon will become another tool. Actually, it is an engineering tool now in some cases. And so we're starting to see this progression, right? Okay, so the G and MGI, the genome, right? So we used to have a joke that there are only two groups that don't like the name Materials Genome Initiative, right? Material scientists and biologists. And of course, it's a metaphor, and we are borrowing the name in some sense from the Human Genome Initiative, which was an attempt, right, to decode the genome. And we're saying that there's the same idea in materials, that there are these basic ideas and building blocks that we can use as knowledge to make predictions. Right? Okay, so what is an initiative in the government? So what happens here is that somebody basically that works in the Office of Science and Technology Policy that reports to the president says, we should have an initiative in an area. And they'll ask the agencies to come up with a plan that says, here's what the government can actually do that's bigger than the mission of a single agency. So here we have the Department of Energy, the National Science Foundation, NIST, of course, where I'm at, and all of the research branches of the Department of Defense. These are very large funding agencies, right, for all the science that happens in the US. And we sit down at a table, we draft up a plan, and then the president announces it. This doesn't mean there's funding. This just means that it's a priority of the administration, and that's an initiative. That's all it is. And then hopefully funding follows from Congress. The agencies then get to work and try to help each other achieve the goals of the initiative. And so I've been coordinating this multi-agency activity for years now, and it's spanned 3 administrations, which is great news. So we're now sort of past perhaps any of the political issues that you can imagine might cause a problem. So that's what an initiative is. Right? So the original initiative was announced in 10 years ago, more than now. And the notion here really was to create the so-called materials innovation infrastructure. And if you look at this simple diagram, you see the basic elements of the infrastructure are computation, experiment, and digital data. Now, these are trivial in some sense, right? This is just science and engineering. And if you do these though, and you tightly integrate these, perhaps more than one is typically used to, one can accelerate the discovery, design, deployments of new materials, right? And achieve good things, right? Clean energy, human welfare, national security questions. And this is a sort of outlier, but it's extremely important. This is really an enabling tool, right? If you build all these infrastructures, you need people to use them. And so the talent piece really gets at a major factor in its achieving the goals of the initiative. And it's also, in my mind, why we're having these conversations, right? Because each country can set up its own similar types of approaches. And it's going to be your workforces, your people that act on these. And a lot of these architectures are going to span borders. And we're going to be figuring out ways to use each other's infrastructures where possible to further each of our goals. So there's a lot of opportunity. So we recently released, as I said, the new plan. If you thought about the MGI in the early days, we were talking about achieving all the way from discovery of a material out to deployment and manufacturing of the material. So this is obviously a very broad range of length scales and time scales that need to be understood. And it's perhaps better to think about it in this picture here, where all of these stages of the materials development cycle really feed back on each other until you get out to deployment, because this iteration that occurs is highly non-trivial, right, to achieve our goals. So when we originally posed the notion of the MGI, we came up with a diagram like this. And if you look down at the bottom of this diagram, you'll see what is the old, you've seen many versions of this probably over the last 30 years, sort of a physics fantasy of multi-scale modeling, right? So you have your quantum down here, and then you're going to work your way up all the way out to a car. Right? So this seems like an ambitious goal. And You're right. If you start with the standard model, right, then you don't even need any adjustable parameters, right? You can just build a car. So this is hard, right? And this is not how it's done generally in science. There are all sorts of inputs that into this loop, right? We decide what data we already know, right? That's going to feed this loop. And then we pick models. None of these models are correct, but we pick them, right? And then we use them in this chain to make our predictions. And if we can do that, then we get a material with targeted properties. Hopefully we've predicted something. And then in principle, as I said, we'd like to even do the inverse, provide the properties, exercise this loop, and figure out, right, what materials you can make with those properties. So really what the MGI is about is developing, creating knowledge, and capturing it somehow in some representation, right? In various databases, machines of various kinds that can be accessed then to make these predictions. So this isn't, as I said, not terribly profound. It's not a new idea, right? There are companies that have been doing this for a long time. But MGI is really about lowering the barriers to doing this. So for example, Apple announced their first version of the watch in 2014. What is perhaps not widely known, and maybe you could go back and look at some of the original ads, is you'll see that they also advertised that the alloys in those watches were better in some sense than the prior versions of the alloys that were used in similar types of things, because they designed new alloys concurrently with developing the design of the watch, making it pretty or whatever. The ability to do this kind of alloy design at the same time that you're developing the new product is highly non-trivial. It used to be that it was 15 years between the development of an alloy and its deployment in manufacturing. Here you're looking at 2. This is an order of magnitude improvement because of the techniques that we're talking about. More recently, so SpaceX has been designing alloys for rocket engines. And it used to be, again, 15 to 20 years to get an alloy into a rocket engine. They're now doing the alloy development in 18 months, which is unbelievable. So it's getting very exciting. But what's also relevant about these companies is that these are multi-billion-dollar revenue companies. So the question is, can we get these ideas pushed down to less well-funded manufacturing, right? So that they can also take advantage of these techniques and we can really help companies around the world. Here's an example of something that's a little bit less exciting than rockets, perhaps, right? Which is, this is motors for a boat, right? So this is the Brunswick. And here you see that they have really engaged MGI practices across the manufacturing floor for a whole range of different metallurgical approaches to building these engines. And again, they see true value in applying these types of tools and approaches. So here you see serious materials modeling going on from quantum mechanics all the way up, playing a role in the design of motors for a boat. So, quite impressive. So the question is, what would happen, right, if we could really get widespread adoption? And so we actually commissioned some economists to try to do this analysis. And as scientists, I'm sure we can appreciate that there are fairly large error bars on this number, but nonetheless, you know, a guess for what widespread adoption would mean is hundreds of billions of dollars of impact to the US economy and probably many trillions worldwide. So, you know, there are simple arguments for doing this. In a certain sense, you could argue we don't have a choice, right? This is the way it has to get done. And so the question is, you know, how do we make it happen? How do we do it well? Okay, so that's the MGI. So I will just sort of summarize here in one slide, right? So the MGI is really about improving our ability to design and deploy materials faster. That's the goal, right? But to do that, we really need better data and models. The MGI is really, in some sense, a direct consequence of our improvements in computation, right? Coupled with the disruptive consequences of the internet. We're also used to it now. But you know, we're going to talk a lot about data sharing. A lot of the activities we're involved in are about data sharing. before the internet, the notion of data sharing becomes this somewhat abstract idea. After the internet, it's obvious. It's like, how come we're not sharing data in a way that is, efficient? And so it's sort of frustrating. And so we'll get into some discussion about that. And so if you then say, well, how am I going to get this information? How this knowledge? I'd like as much of it and as high quality as possible. I would say there are three sort of basic ways, right? There's high throughput computation, and there's a lot of that going on. The Nomad example here is an excellent example of it. And of course, there you really need to trust the models at some level, or you're wasting your time. You could do a lot of experiments. This is a non-trivial proposal. Experiments are hard, right? Or you could try to get it from everywhere. And what does that mean? Well, that means you have to somehow go into the literature and look at the published data. But if the data isn't published, then you have a problem. So we really need to think about how we could change our models for publication, and we have some ideas there. Okay. So in 2013, in response to the federal initiative, NIST said, well, what will we do in support? And so here's how we framed this, looking back in time. And so this should look familiar, right? So here is our sort of vision of what the MGI looks like at NIST. And then we said, well, here's what we can do to support it. We said, we're going to make our support of the initiative focused around data, right? Because this is NIST has been delivering high quality, high precision data to the world for its entire history, right? A big fraction of our metrology work is really around adding, that extra decimal point of accuracy to some quantity of interest and providing people with the best practice to do that. So we said, okay, we're going to focus on data quality, give people the tools to assess whether or not these new kinds of data that are being distributed are any good, right? How do you know, right? Is it garbage? Where is it from? And so a lot of questions there. And then we also realized we were going to need to think about how we move the data around. How do you exchange the data? And when we started to think about exchange, we thought this was sort of technically kind of boring, not so scientifically interesting, and mostly technical. It wasn't very challenging, right? We would figure it out. And of course, this was incorrect. This is an incredibly difficult problem, and most of us are focusing our energy now on this. There's a lot of issues in exchange that have to do with human behavior and social issues. And so we're going to talk a lot about what motivates scientists to get better solutions, to get to better ways of working, essentially. And then ultimately, we believed that we would get to a place, if we had this infrastructure, where we could have new methods and new measurement techniques that were data-driven. So we're going to end up talking about data-driven analysis. Now, when we wrote this in 2013, if you would ask me when these types of approaches, which are effectively artificial intelligence approaches, would become prominence, I would have said, well, that's probably a long way off still, 10 years, 15 years. And instead it was 3. So things have changed very quickly. And I'm going to talk some about AI and how it's now driving the initiative and the way we think about it. Okay. I should also mention that we set up a center funded by NIST, which is a rare thing because NIST is not typically a major funding agency. We have a little bit, but most of our funding goes just for the labs, just like many of the institutes here. So we set something up in combination with the University of Chicago and Northwestern and the Argonne National Laboratory, part of the Department of Energy. And they had this mission to sort of support the MGI to build a materials data facility, which you can take a look at, anyone in the world can use, and build up all of these different use cases as ways of proving out the ideas that are the core of the MGI and materials design. So just to give you an idea of how that works, I have an example here for a nanoelectronic material use case of materials design. And oh, by the way, I'm going quickly. Anybody who wants the slides, I'm more than happy to share the slides. So just send me an email and I'll send you a copy of a PDF. So, right, so here's an example of a use case. And the only point here, right, is the classic material science paradigm, moving from the left processing to structure to properties, and then all the way out to how the material performs once it's been put in a device of some kind. And here, you know, each of these ideas, whether there's the internal structures, you know, what the band gap is of this material, whatever it is, are linked to the other, you know, areas through these lines, but these lines are nothing more than models or databases, right? That's what it means, right? That you have some predictive power that gets you from one to the other. And so materials design is really about exercising all of these models to get you from here to here, or ideally even from here to here. And we're going to talk about AI, but we'll save that for a little bit. Okay, so this piece of the talk, I started giving in 2010, and actually in some ways before that, because I was trying to explain to some managers initially, before even the MGI, what the relationship of modeling was to measurement, because there was some confusion, in my opinion, about this. And it gets at a very important idea that links, I think, all of these things together. So forgive me, it's a bit pedantic, but I hope you'll find it interesting. And then also what it means in the context of artificial intelligence. So I use this example of a so-called tensile test, right? And this is an expensive machine, an instron, and essentially all you're doing is putting something in this system and pulling on it and seeing when it breaks, right? It's a very basic type of measurement. And the typical way to do this would be, right, and you'd say, oh, well, I want to measure the modulus of this material, right? I want to, whatever that happens to be. And then I'm going to measure the strain. And then I'm going to record those values. And most engineers would tell you they, you know, use Excel. That's their weapon of choice. And if they like the answers, they might publish them. And that publication effectively is the metadata, right, for that experiment. And of course, yeah, right, here's the point, right? Well, what's a modulus? They're not measuring a modulus, right? The modulus, well, more than the modulus is in this tensor, right? They're assuming this is true and that they can use a linear elasticity Hooke's law, right, to relate the stress and the strain. And of course, that's not right. So you're not measuring the modulus, you're measuring the strain and assuming this is true. And so when we talk to experimentalists and theorists, need to be very clear, right, about the fact that we know our models are wrong, right, but they can be very practically useful, but that you can't really make a measurement except for some very basic things, in some sense, without a model. And even there, and so let me show some even more fun examples. This is my favorite one in the last 5 years. Right? So it's Nobel Prize, I think, 2017, right? So this is the LIGO, right? So the gravitational interferometer. So you have two arms, these are several kilometers long in each direction, and you're running a laser down them, and you're effectively detecting the distortion in space-time due to gravitational waves by measuring the change in length of these two arms. Now, I don't know, does anybody here know what strains LIGO can measure? It's 1 part in 10 to the 22nd power. So it's a very small strain, right? It's less than the radius of a nucleus of an atom. And so what they said they measured here was two black holes spiraling in on each other, 1.5 billion light years away from Earth, or, you know, so 1.5 billion years in the past. But of course, they didn't measure that. What did they measure? Right? What they did was they took Einstein's equations for that event and put it on a supercomputer and computed what the signal would have to look like for two black holes spiraling in at each other 1.5 billion years ago, and the signal coming in towards Earth. And then you compare the signal coming out of LIGO with that computation, and you're able to do a measurement validating Einstein's theory if the shapes are the same. If it's not, you haven't made a measurement. You don't know what you're looking at. And in fact, they also have to correct for the other effects on the ground, right? They have 2 copies, or now 3, of this instrument in different places on the surface of the Earth, right? So that you can deal with perturbations associated with local environments, or a truck driving by or something. So it's an amazing experiment. But the point here is you can't measure without a model. Here was an example I found from some calculation where they included the defects in the system and were able to improve microscopy because they had a better understanding of the sample that they were looking at, right? So again, you can continuously improve. Probably in the last hardcore physics example I'm going to include here, right? So this is the Large Hadron Collider, another Nobel Prize, right? And here they're looking for the Higgs, and this thing generated, and it's probably inaccurate now, right? About a petabyte a second of data. Now it can only save a gigabyte a second, which is still a lot. But how can you get a data? That's 6 order of magnitude data reduction. How can you get such a great data reduction? And the answer, of course, is the standard model is right, basically, as far as we know. And so if all you're looking for is the signal for what is different, right? What's new. And so you can throw away everything else. And so the only point here is if you have a really, really good model, you don't need much data, right? But if you're working perhaps, say, like in biology, you may need to save all the data, right? Because you don't really have a fantastic model of that system. And so you're looking for deeper correlations. And so I think we could all agree that it's somewhat naive to say for these incredibly complex systems that we are interested in, that we couldn't learn something from the biologists, right? Where we just don't always have the models that we want. And we could use a data-driven approach. So we would like to somehow take the best from all of science here and do a better job. Okay. And if you think about a physics model, this is where it starts to get very subtle, right? All a physics model is saying we've done some experiments and here's a small equation that seems to explain a lot, right, that we've learned. So that's similar to something that we're going to talk about with AI. Actually, the differences are subtle and quite interesting. There's a study that just came out looking at the role of artificial intelligence in materials discovery. I mean, this is like less than a month old. It's free to download. I recommend you grab a copy. It has all sorts of recommendations and also the implications for manufacturing. We're certainly, NIST co-funded this study, and we're certainly very interested in trying to figure out how to act on this study. Okay, so I'm going to talk a little bit more about how the AI, artificial intelligence, impacts the MGI. Because in the end, what is artificial intelligence but another system for generating models of things, whatever that is. Right, so I love this example, and I first saw it in some version in 2015, and I must admit the first time I saw it, I was absolutely confused. It seemed like what they were doing was nonsense, and it was very confusing. And then as they walked me through it, my eyes were opened to enormous potential. So in this case, what did they want to do? They wanted to try to predict the phase diagram of a ternary alloy. Okay, so they wanted to know where, as a function of 3 different compositions, in this case, cobalt, nickel, and iron, where essentially the crystal structure changes as a function of that composition in equilibrium. And it'd be nice if we could quickly get all of these phase diagrams quickly from a set of experiments. So this is a fairly expensive way to do this, but it was very interesting as well. So what they did was they created essentially a combinatorial set of samples of all of the different, or maybe 500 compositions, and deposited them on this silicon wafer. Okay, and then they took it to the beamline at Stanford, SLAC, and they put it in the beamline. And then, of course, you're looking, essentially doing X-rays on this system, and you just scan the X-ray across the system, and what happens? You'll get various scattering patterns, And as you move it across, the pattern will change if there's a phase, if the phase changes. So if you think about what an AI is good at, it's not going to tell you what the phase is, but it can do a really quick job by image analysis of telling you if there's a change, right? Because it's good at, instead of cats, you're doing X-ray scattering diagrams, right? And so you just move across it and it goes, ah, there's a change. And so you could just scan the whole thing and find the phase boundaries. And so suddenly you have used these pattern recognition systems to characterize an entire phase diagram. But it gets better than that, okay? So once you started to think about this, now you can start to say, let me use Bayesian techniques to say, well, what is, instead of scanning the whole thing, that's dumb. Instead, I'll just take 4 starter points. And now I'm going to do a search, maximize or getting rid of as much uncertainty as possible. So I'll say, where on this diagram should I look next to improve my understanding of what I'm seeing? And this red dot that's hopping around here is the algorithm's attempt to say, okay, I'll go look here. Okay, now I'll go look here. And then we'll keep improving the diagram. And this curve here shows you the rate versus just a standard scan of their ability to lock down with this phase diagram. So you're like, oh, well, that's nice. They figured out a smarter way to do the scan. But it's better than that. Because now, if I tell you, okay, I should look here next, but look here, you could do something different. Instead, you could synthesize there. And so instead of making a whole sample with all of the different compositions, you just synthesize the next one. And so now you've closed the loop and you are doing autonomous generation of phase diagrams, where you have robots in the loop to do the synthesis. The AI makes a decision about what to synthesize next, and you are potentially massively accelerating the materials design. And as you might imagine, of course, you don't just need to do this for phase diagrams. If you now look in the chemistry space, this is happening, right? So I cannot imagine that the major chemical companies worldwide are not using these techniques for, say, small molecule chemistry, right? Because you just can keep iterating these and putting robots in place to do these types of experiments. Now, and you can also imagine using these autonomous systems, not on a beamline, but of course on your own laboratory X-ray machine or whatever. So very exciting. So here's an example of some work that was done at NIST, right? Here's that standard set of linkages between processing to properties. And this was actually for designing the US 5-cent piece, which unfortunately is called the nickel, although it doesn't have much nickel in it anymore. But we were trying to design a new alloy precisely because this alloy was too expensive. It cost more than 5 cents to make one. So it didn't make any sense, right? So, you know, here are all the properties that you want. You want it to not wear out in your pocket. You don't want it to corrode. So there are all of these requirements on the new coin. And the most interesting one is electrical conductivity, which I didn't realize, because this is, so it works in vending machines. This is how they detect counterfeit money. And so you need to get all of this right, and then we designed a new alloy, and we're hoping that eventually it gets adopted. Although who's using money anymore? So, you know, that's a whole nother problem we didn't anticipate. But okay, so what's also interesting, and the reason I showed this, besides just talking about some interesting materials design work, is that you can imagine, again, eliminating any or all of these arrows and replacing them by an AI, okay? Because that's a model, right? So now you're just saying, do I have a model? Well, if I don't, I can develop something data-driven. That would be one reason to use an AI. And another reason might be that it's 1,000, 1,000,000 times faster. And so it might allow you to explore space much more quickly than you would otherwise. Now, many of you probably would agree that there are some risks associated with using AIs. So we can have some discussions about that as well. But let me just talk a little bit about the MGI strategy. And then I'll talk about some other issues that are sort of keeping me awake nights. And then I'll be done. Okay. So these were the 4 goals of the MGI strategy in 2014. And probably the most prominent goal at the time was listed first, was leading this culture shift in material science research to encourage and facilitate integrated teams, because it was really a team approach that was going to get this integration done. It's too much work for one person. The rest of the goals are going to look pretty familiar to what was called out in the original white paper, which is we need to get this integration of computation and experiment well done. We need to think a lot about materials data, something that really basically nobody had been thinking about except in a very simple way. And then, of course, education, right? Training. If you now go to our newest strategy, which was released 4 months ago, took quite a long time to get this done. You'll see that we still have a discussion on the infrastructure, but that paradigm shift is gone. And it's because we really believe people understand this now, that there's really not much debate, that if for large classes of research, if you want to get engineering impact, you need to really work with other people. You can't just write a paper and hope someday someone notices it. It is better to work with people who care about your results and get the results integrated up the line, and preferably even figure out ways to get the machines to talk to each other and get the human out of the loop. But beyond that, right, we really need to think hard about how to unify this infrastructure. So now we are all building pieces of it. And how do we get these pieces to talk to each other to get the predictive power where we want and lower the barriers to access further, to use these tools? And now, instead of just saying we need to share the data, we're saying, how do we harness it? How do we use it, right? And this is mostly about AI, the second goal, and about deploying artificial intelligence, not only in research environments, but also in manufacturing. And then finally, again, we're still talking about education because this is an outstanding question. And a lot of what we're talking about are relatively new approaches for chemistry, physics, material science, and engineering across the board, right? And so we somehow have to modify the curriculums to reflect these new approaches, okay? So in terms of data, which we're gonna have a lot of discussion about, I have some highlights here. Right, so it's one of the objectives here was we need to build out a comprehensive data infrastructure, which includes tools, standards, and policies that encourage fair data principles. So it was really neat to see FAIR called out explicitly in a federal strategic plan. I don't know if it was the first one, but it was certainly one of the first ones to do that, and and bolstering these infrastructures. And in particular, we want to foster a national materials data network. And by this, we really mean actually international. There are some politics there. But in general, we want broad collaboration amongst the communities to drive the creation of this infrastructure and figure out what it is that we need. And then also accelerate adoption by finding challenges that are at minimum national, but probably global. So for example, climate, where using these kinds of approaches can help advance our ability to mitigate some of the problems that we've generated over the last few hundred years. So, and then beyond this, let's see, we have getting FAIR to make data so-called AI ready, and a variety of other, let's see if there's anything here I want to emphasize. Anyway, as I said, if you want a copy of this, I don't want to read you the whole slide, it's boring. And there's education as well. Okay. So let me finish up by talking more about how we get more data. And this gets to a less than technical issue, as you'll see. See how we're doing on time? Excellent. Okay. So in 2017, there was another study put out, which was called Building a Materials Data Infrastructure. And it had a variety of recommendations for what the materials community could do to improve the data infrastructure, materials data infrastructure as it stands. And so what MDI there is materials data infrastructure. So the first recommendation was strengthen the materials data infrastructure core in repositories, registries, tool development. And I think a lot of us are doing this. This is happening and it continues to improve. So good, we're working on one, right? Two, sustain and grow the materials data infrastructure dedicated funding programs. Yeah, I think we're doing that. At a minimum, we're sustaining. It hasn't gone backwards. So good. So we're doing two. Now, three, create, execute, and monitor incentive mechanisms. Nope, we're not doing it. Okay, in my opinion, or if, at best, it's weak. And so the question is, what can we actually do about, and people will come up to me and say, how do I get people to share their data? I think it's the wrong question. And I want to talk about that more. Okay. And it said, what's stopping us, right? It's because nobody has an incentive still, by and large, to share their data, right? And people complain about this and, yell, right? But this isn't sufficient, right? We need to solve the problem. We need to think about what it is that needs to happen so that we are sharing more data where possible, right? And so there are a number of reasons that this is not happening. So the most trivial one in some sense is lack of information about how to do it, right? And so if you don't know, you can't do it. It's trivial. Right. The second one is technical. Right, it's sort of, I don't know what tools are available, so even if I wanted to and I thought it was a great idea, I don't know what to do, and Google searching isn't helping, right? And so, at NIST, we modeled our tool development off the astronomy community. We brought in the head of the US Virtual Observatory to head up our materials data infrastructure thinking. This was a nice example from the Hubble. The Hubble telescope, where I don't know if you're aware of this, but basically if you're in high-end astronomy, you can get access to all of the data from all of the major telescopes in the world by accessing the virtual observatory. You just need to know the position in the sky that you're interested in, and if you want, you can specify a frequency range and get all of that data. If you look at the Hubble, approximately 2/3 of the papers written using the data from the Hubble were papers written by people who did not take the data, right? So they're just using the data that's been collected by other people and then doing their own research. So this is pretty cool, right? You're starting to see the availability of data actually furthering research in a way that it otherwise couldn't. So here was an example. Astronomy, you could say, is significantly easier than materials in terms of dealing with this problem, right? As I said, you just need the position in the sky and the measurement type, which is basically the wavelengths of interest. Whereas for materials, you have various metrology, various measurement types, but there's all of these processing conditions that you need to know as well. And so you end up with a significantly more challenging problem. But it's not impossible, it's just bigger. Right, so we have a lot of work to do here. Pick a square, get to work, right? But we can ask the question sort of, what is, oopsie, that back button is dangerous. What is our telescope, right? So what are the driving forces to get us this? And of course, I think many of you would probably agree that it's the beamlines, right? It's the synchrotrons, it's the neutron sources. These are generating large amounts of data now, still growing geometrically. Because basically of Moore's law, the detectors keep getting better, and this is expensive data. If you've ever worked at a beamline, you have to get a grant basically to get time on these things. So it's like a telescope, right? And so it's sort of generating this, and so this can really be a place where they are thinking very hard about data infrastructures. In fact, they're running into the same problem now as like the Large Hadron Collider. They can't save all the data that's coming off the machines. And so they're running into some interesting challenges. So yeah, let me skip that. Okay, So that just sort of get at tools, right? And everybody's thinking about that. In terms of the biggest issue, in terms of incentives, it's professional, right? It's your career, right? So people are influenced by incentives. And so our behavior is almost completely driven by, you know, what it is in the context that we're in and where it is that we're rewarded in various ways. And so I love this example. So I don't know if people are familiar with this. This is the story of Galileo, who obviously fairly well known. And one of his most important discovery arguably was discovering the moons of Jupiter, right? So he showed that a different heavenly body, right? There seemed to be the laws of gravitation behaved the same around Jupiter as they did with the Earth-Sun system. So here you're sort of a microcosm. So he had also then pointed his telescope at Saturn, and this was his first diagram of that. And he thought he saw new moons. He was seeing the rings, actually, but he couldn't resolve it. But so what he did was he published a 37-letter anagram, right? Just a series of letters, probably was Latin, right? To describe what his discovery was, that he could decode if somebody else pointed their better telescope at Saturn and tried to say they discovered it. But he could prove that he discovered it first without actually tipping off his competitors, right, that he had done this. So I believe most academics would do this if they were allowed to. Okay? The reason we don't allow it is because it would be a disaster, right, for science, right? So the patrons of science, people who pay for it, wouldn't permit this behavior from anyone that is getting a federal grant, right? So there are rules that are in place that we have developed over the centuries for the way we do science. And we need to change those rules in general to get to a better place. But of course, we also need those tools so that people can follow the rules to the maximum build. But it even goes further, right? So this gets it fair. So how do we get there, right? I would claim the answer is simple. I think we need to think about this problem from the other side. Instead of saying, well, someday you'll be able to cite my data and this will make things great, and everyone will give me credit and tenure at an important university because I shared my data. Instead, let's ask the question, what is it that scientists and engineers want to do, right? And the answer is science and engineering. It's not complicated, right? So if we can answer the question, what does a platform look like that allows people to do things that allow them to write the next paper or design the next material, right? Can I take my data, put it on a platform, combine it with another data set? Can I build off prior work? Can I visualize my results after I put that data there in new ways? Can I discover interrelationships in the data that I would otherwise not be able to do unless I put the data there, right? Can I use artificial intelligence techniques on this data to get new insights into correlations between the various parts of the data set, right? If I can do all of these things, if I can find new collaborators using these systems, I'm going to want to use them, right? And then as a side effect of my use of these platforms, the data is shared and other people can build off my work. This is how we will achieve these goals. So it's not that anything that we're currently doing isn't leading towards this. It's that we need to keep these ideas at the front of our minds, right? We are headed towards this, and we need to think about the ecosystem where these platforms exist. And we need to turn around and talk to the people who fund science and say, this is what we want, right? How do we get there? We're missing pieces, right? And we need, as a community, need to talk to those people. So, you know, I like to say, this will bring you fame and fortune, right? These are the things that scientists care about and we as researchers care about. And then I was talking to Claudia yesterday and she pointed out there was another one which I forgot about, which is, of course, the joy of exploration, which is a lot of us are in this business because science is cool, right? And this isn't mooted by this because, of course, all of these capacities are also new ways to explore, new ways to look at the world. And so I think that there's, it's just more of the same. We want the tools to get the work done. So to do this, in my mind, we need to create this data network, right? Because again, we need to drive this story. We need to have this conversation around data and what these infrastructures look like. And so we need academia, industry, government, worldwide community to drive the development of these infrastructures, which will hopefully lead to more funding, because what we're talking about doing really is billions of euros a year. It's way bigger than the funding that we're currently getting, a few $1 million here or there. Not that we're complaining about that funding, but we really need to think about taxing ourselves. And if you think about the R&D expenditure in materials alone, it's a lot of money. It's 50 billion a year in the US minimum. Okay, so if you thought about a 5% tax, you're talking way bigger than the amount we're spending. Okay. So we're thinking about something called the Materials Research Data Alliance now. This is a collaboration of a large number of US universities and government in the US, but we already have international participation, and there's really no boundary here at all right now. So it's just an informal alliance. It has no power to make anybody do anything. If you want to set up a working group here, you have a specific area or technical interest that you think you would like to bring the community together around, it forms a nice umbrella and could be a nice example of the kind of thing that a national materials data network would be an example of. So with that, I will stop and thank you for your attention.
That's fine?
Yep.
Okay, good. Thank you very much for this great talk and insight in your thinking, which in fact, I think is essentially the same as we are thinking. I don't see really a big difference there. So I could invite first maybe some questions from the audience. Actually, let me first explain. Actually, my name is Matthias Scheffler, and I'm just following Claudia because she had to go to another meeting. So I'm leading really the discussion. So we start maybe with a question from the audience and then actually from the Zoom room. I could start with one little thing and to get it warm up, and then so understanding that a little bit better. I mean, the White House initiative is an initiative really from the president, and actually several US presidents have done so. I mean, you and I were probably affected by Clinton's nanotechnology initiative, which had really big influence. Bush had in 2003 the hydrogen fuel initiative, which only is catching up now, I would say. And of course, actually, the Materials Genome Initiative has a big effect. But these initiatives usually come really without money. I mean, it's really just an initiative from the president's office. And my question to you is, because reading the first one and also the second one, they're really written very, very well, I think. So can you just explain how they really are created? How much is really the active scientists involved in their, say, the National Academy or the American Physical or American Materials Research Society? I'm not completely sure how much they are really involved in developing these things.
So, okay, so let me tell you how the MGI was developed. And actually the National Nanotechnology Initiative, which you could argue's timing was better because it was actually written by Clinton's administration, but then the Bush administration was the first to fund it because it happened right at the end of the Clintons. And so it shows you how the politics were not quite as crazy
as the people
as they are now. But also it shows you that science has largely avoided some of the politics, which is good. So in both cases, the NNI and MGI and any others, there was a BRAIN initiative. There's been lots of initiatives. As you said, right, the president, they decide it's important. And so the question is, how does this get developed? In the case of the NNI, the same person, Tom Khalil, who worked for the Clinton White House as well in the Office of Science and Technology Policy, which advises the president. They pretty much are wandering around various meetings, looking for ideas they think the administration, the president, can sell to Congress, right? Because they have the money. And so they come up with some idea, and then they approach the federal agencies that have a scientific portfolio and ask them what the government agencies can do. Now, so I was one of those people in the case of MGI. So NIST, my agency, sent me downtown to work with my colleagues across government. So the people in that room are all feds, but they're also all scientists, or they at least used to be. And they're all members of the professional societies that you membered, and they all have colleagues. And if you take like the people at the NSF, right, they're funding hundreds of millions of dollars in research portfolios across academia. They know all of the players, and they know all of the research that they're funding. So they're plugged in to what's hot, as it were. Now you can criticize. I mean, it's not going to be perfect, but that gets at sort of how the government is informed when it writes these plans. Does that get at the question?
No, I mean, I was amazed because I was on one of these workshops organized by the National Science Foundation, but I felt actually the thing was already written then. But it was still actually, I mean, maybe they just wanted to be confirmed, right?
So they did have almost, there is a process where after the first draft is written, then there's an opportunity for comment. And so that's probably the activity that you were involved in. So you're right, it was probably already written, but it was probably also subject to some modest modification.
No, I'm just surprised how this really works, because
well, we don't want, the National Science Foundation is governed by what's called the National Science Board. See, this is the stuff, right? Each country is unique, right? The National Science Board is very famous people in academia mostly. So the NSF can't do anything that they don't like. So it's very, very much follows the community in terms of its behavior. So moving into some of these areas is risky for them.
Okay. Just actually again to the Zoom people, if you really would like to ask a question, if you raise your hand would be nice, then I see that, and we can really then unmute your microphone. Now, Christoph Koch has a question.
So you mentioned that you want to have money.
Of course.
If you were given to spend $100 million at NIST for MGI.
How much? Say it again.
100 million.
Is that how much we're spending now?
No, I'm just, if you were given an additional, you now, yeah, that's the question. You were given an additional 100 million. What would you do with that?
That is a great question. It's like you're my manager. Okay, so let me see if I can come up with a few answers there. So there are a number of things that I would do with that money. Now, is that per year or one? No, I'm serious.
No, once.
Oh, that's not enough. Oh, no, this is not as good. Okay, right, because there are things that you can do with a lot of money that you can't, that don't make any sense with less, right? For example, building a world-class computation center. Okay, and this doesn't have leadership class computing like the Department of Energy. So that's one thing that's an easy call. We need to make major investments, right, in the community, but this is actually small amounts of money, right? Millions of dollars a year. The most important thing is thinking about the full data infrastructure, setting up platforms that are useful, and then working with industry where appropriate, if you can let the markets take care of some of these problems as well. And so what I would probably do is set up centers, public-private partnerships that can bring in academia, that can bring in industry, right, to work on these problems and deliver the infrastructures that are needed. And you could spend any amount of money on that you want. And the more you spend, the more impact you'll have.
Let me just actually modify that question a little bit.
Okay.
I mean, in the beginning, as we said, there was no money, but of course there was the request that all the funding agencies should dedicate some money to that. So how much money does the MGI, but actually also maybe the related activities, say data centers and also the infrastructure, which we still have to build. How much money is there in the US every year?
So it's a question of how you label it. So this is a non-trivial question because you could ask NSF, for example, and they would give you one answer for how much they spend per year on their very specific MGI program, which is called DMREF. It's a long acronym, but it basically run out of their materials research division. And that's, you know, I don't, 50 million a year or something like that. But then they have their education programs that also fund, you know, millions a year. So you could come up with a number, and then you go talk to Department of Energy, and they have materials and chemistry software institutes that they would say, yes, this supports MGI. And so you could find, and then is the beamlines MGI or not? I mean, so it becomes, it's hard to measure.
I mean, it's getting MGI as soon as the data are getting also characterized, right? Because the data, if they are not characterized, are not very valuable.
That's right.
Actually, they're useless.
That's right. And so,
but actually, you've forgotten NIST. Actually, NIST is also
right. So NIST, we're spending 20 million a year. That one I know because that's me. Right. So we have 50 million a year in programs that's permanent, and then 5 million a year that's supporting the center.
More question from the audience? Do we have anything from the Zoom? I don't see anything at the moment. There's one. Okay. Yeah, Oliver Heller. Can you? Oliver, can you talk?
First of all, thanks very much for the talk. Very interesting. And it gave me also lots of ideas I can use to communicate our problem to people that are not very into it. So thanks very much for that. My question is about IT technologies like ontologies, knowledge graphs, and knowledge graph embeddings or predictions to manage our material science knowledge and the data and models, and to make them communicate with each other. Is that something that you're looking into? Is that meaningful to you?
Yes, very much so. So I have, we initially had a large ontology effort. We sort of stepped back from the ontology effort because we couldn't figure out a way. It was too big, right? All of materials research is too big. That being said, we have a large effort in schemas and schematization of materials data, and a lot of the informatics issues around that. A lot of this, you know, efforts are US wide in various kinds of new data structures to describe either processing of materials or characterization and things like that. So more structured data, better metadata. Yes, this is a huge fraction of the data effort at NIST. When I mentioned the 3 areas, right, the exchange piece is all about the kind of thing that you're talking about, software tools to do that and things like it.
All right, thanks very much.
Yeah.
Thank you again. So I did not get if there's already a success model. So locally, right? An institution collecting from different machines and, you know, something working like a hospital in a way, right? Very expensive machines collecting a lot of data. And then there's a chief data scientist who to be an MD looking at it and putting another story out of the different individual stories.
Nice, yes.
So is there already something, an institution working like a hospital in academia in a way?
I think certainly not at the level that I want. I saw a nice example here yesterday of what's going on at FHI that is starting to look very exciting. So I want to follow up on that some more. You know, it's not a race, but I would certainly like to see that kind of a model adopted in other places. I think probably we will see certain models adopted at things like the DOE labs first. Again, they are more top down. You can say, you know, that if the manager of DOE lab says we're doing this, you're doing it. Whereas if you say this in academia, it might take a while. So in terms of places, actually, one of the places we did model was from the National Renewable Energy Laboratory. You'll tend to find large labs where this has been done. right? They've essentially connected all the machines in a good way, and the data that's coming off them is in some sense well captured. Getting good metadata is still a very challenging intellectual problem, right? But nonetheless, so there are examples, right? How successful they have been is an interesting question. A lot, again, that has to do with this question about utility. So it's one thing to say, I'm going to capture all the data and metadata, but somebody needs to use it somehow, right? They need to do better research with it. So it's that next step that is often missing. And so it's creating these small stories where by doing this, you actually moved science or engineering that matter. And they're out there, but they're not as many as there should be.
Okay, I think there's one more hand up. Did you? I don't see that. No?
It was an email.
Okay. So I think actually it's also probably time to close. So actually, before I thank him, I mean, just actually, so there is also, in fact, a collaboration. So we have a memorandum of understanding with them. So there is this association, FAIR-DI, Fair Data Infrastructure, and which was there before, FAIR-MAT was there, which is an international association, an eingetragener Verein, which is gemeinnützig, but that has a memorandum of understanding actually with NIST. So there is actually, and somewhat Corona came in between. In principle, we should actually have exchange of people from Germany, from Europe, in fact.
It would be wonderful to have people.
And really exchanging ideas and really working, because we are working on the same questions. Right?
Absolutely.
And that's really great. So thank you again, actually, for being here, and let us intensify the collaborations.
Indeed, let's work on that.
Yeah. Thank you very much.
Thank you again.